All right, ladies and gentlemen, today I'm excited to introduce to you what is a brand new number. So we're going to introduce the number called E. You've maybe heard of it a little bit before. And the goal here is really to understand where this number comes from, because using it actually is pretty easy after we've done the work that we've already done, right? So to do this, I've given you a table that I had you fill out in a previous lesson. This is that context where we're investing $1,000 at 100% interest, which is pretty nice, right? And I gave you all the values of the table printed, and then I want you to just write down the simplified version. So all I did here, just to be clear, is I took my exponent and I applied it to the to the base, to the 1.092, right? So this is equivalent to this, right? And I did that all the way down because the goal here is to look at the trend of what's happening to these numbers. And I would say it's pretty clear here from the trend in the table is that this pattern, as we make our n bigger, right, as we compound more frequently, we're getting closer and closer to like 1,000 times about 2.7. So this is the trend, right? We shouldn't really say equals there, should we? We should say we are approaching 1,000 times 2.7. And this number is kind of like pi, right? So pi is a weird number. It's irrational. It kind of pops up out of thin air when you're working with circles, right? Here, same thing. We have this number 2.7 that is the result of a trend as we make our compounding periods bigger. And like I said, this number's name is E. It has a button on your calculator, and it's like on second natural log, you can see it says e to the x there. And then your calculator kind of automatically puts you in the exponent. And that's because this number is used very, very frequently when dealing with exponential relationships. So I'm just going to put an e to the 1, just so we can see what that number is according to our calculator. And it's like 2.71, right? So we can say that this relationship is really 1,000 times e, right? And obviously, if I did 2 years, compounded for 2 years, it would be e squared, et cetera, et cetera. Okay? So we have a relationship between our previous formula and this current formula. So our previous formula was we had our principal times 1 plus r over n to the nt, right? And our new formula, often we say PERT, but it's p times e r to the t. And the key word here is continuous compounding. That means we compound an infinite number of times, right? We keep compounding. So it's not daily or weekly anymore. It's like every single moment we are compounding. And this is like weird and abstract, obviously. We can't actually count an infinite number of times of compounding, but we can, using this idea of a limit, right, actually use that abstraction to do calculations. So the relationship here is if I take my original compounding interest formula, it is equivalent to my PERT formula when I take the limit as n goes to infinity. So I'm letting my compounding periods grow increasingly numerous, right? And you don't need to understand right now the algebra behind this limit, like how I would rewrite this to take this limit. You just need to understand how to use the formula. So we're going to do a couple of examples on the next page. So we have a continuous exponential growth model as a keyword in the text of our bacteria problem. Notice these problems are like similar contexts that we've already been dealing with. This tells us specifically that we're continuous to use our PERT formula. And our equation would be just something like f of t equals 1,800 starting value, right? We used to call that a, now we call it p. And then my rate is 0.081, so my rate is still a percent. So here's my r. And then to the t. So not so bad. And then f of 6 for 6 hours would be 1,800 e to the 0.081 times 6. And then I will show you how I get that in the calculator. So it would be 1,800, and then I'm going to do e, and then 0.081 times 6, both in the exponent here. And we get 2,926 bacteria. And let's make sure we round correctly. We round down to the nearest whole bacteria. Okay. So that's pretty easy. We're just plugging into a formula, right? The other thing we can do is rewrite in terms of a simple exponential growth model. So that means our base, if we want to know the hourly percentage increase, we want to rewrite it with just our base, right? So that would be something like this. So the idea here is I can rewrite these models in a bunch of different ways depending on what I want to know. So I can kind of break it up like this, because if I multiply my exponents, I would get what I got before, right? And then I can use my calculator to solve for that exponent, right? So I'm just going to be like, okay, what is e to the 0.081? And that gives me 1.84. Did I say that right? 1.084. And this would be per hour, right? Because t was in hours. And our hourly percentage increase, well, if it's 1 plus r is 1.084, we would have then r would be 0.084, or an 8.4% increase, right? And notice this 8.4%, it's a little bit bigger than 8.1%. And that's because we're compounding continuously. So compounding continuously causes a function to grow very quickly. So it makes sense that our just hourly increase is going to be a little bit bigger than the continuous rate that's given to us in the problem.